2 days ago, we learned to deal with position time graphs, the shapes of those position time graphs, but also mathematically how to find several things on those position time graphs. I'm going to plot that graph right now, or an example of a graph right now. Position on the y-axis, time on the x-axis. That means position would be my responding variable, time would be my manipulated variable. I'm going to draw the graph looking something like this. We'll make this 10 seconds. This one is 20 seconds. This one's 30 seconds. Not to a very good scale, clearly, but that's okay. We'll make this 5 meters, and we'll make this 10 meters. What's the title of this graph again? I mentioned it a second ago. But probably forget what I said or didn't even hear it. Based on what you see up here, what's the title? Position versus time. Always y-axis versus the x-axis. All right, we can find a number of things on this graph. Now, one of them is position. At any given point, I can find the position. How do I find position? How do I find position at, say, 6 seconds? How do I find position at 15 seconds or at 30 seconds? 3 words. 3 words. Karen? Up and over. So if I want to find the position at 30 seconds, go up and over. Looks like it would be about 5 meters, right? Next thing I can find is the displacement. What do we define displacement as? Ashley, do you remember? Look at the symbol if you don't remember. Look at the symbol. What does delta mean? Yeah, okay. Change from start to finish. And what is D? Same as this, right? Which is position. So change in position. Change in position. Displacement is the change in position. So how are we going to find the change in position? Is it? Up and over, and then you're going to do what? Subtract the 2. So in other words, you're going to find 2 different positions and then subtract the 2 positions. All right, good. What about the average velocity over an interval? If it's a straight line, how do we find the average velocity? One way, but really there's 2 ways of thinking of it. Check. You can say it's the slope. If it's a straight line, you can say it's the slope, which is delta y over delta x, or rise over run. But there's another way that we can think of it, but it's really the same thing. Yeah, delta y over delta x, that's the slope. Okay, but what's the same thing as delta y over delta x? Sebastian? Displacement divided by the time, right? Delta d over delta t. All right, straight line, either way, that doesn't really matter. The slope, delta y over delta x, or just the equation v is equal to delta d over delta t. Now, if it happens to be not a straight line, then you can't really find the slope. Then you've got to use delta d over delta t, the displacement divided by the time. And finally, the instantaneous velocity. The velocity at one specific moment in time. You can only do this right now, by the way, if it's a straight line. If it's a curved line, you don't know how to do that. I'll show you in a few minutes, but right now, you can only do it if it's a straight line. If the average velocity is 1 meter per second for this interval here, this first interval, then the velocity anywhere along that line is 1 meter per second. It's the same as the average velocity unless it's not a single straight line. And then if it isn't, you don't know how to do it. Okay? All right, let's take a look at the work that we were doing on that worksheet here. I want to do question number 4. I think we already did question number 1, correct, in class? Any others? 2, 3? Want to do all of them? One of them? Both of them? Besides number 4, which I want to do anyways? Okay. Let's do all of number 2. So number 2 and number 4. Here's number 2. It says, what's the displacement between 0 and 10 seconds? Displacement is final position minus initial position. So we're going to say it's df minus di. The final position is 0. The initial position is 14. negative 14 meters. Don't forget the negative. It's sloping downwards. It's a constant velocity, but it's sloping downwards. So it is a negative displacement and a negative velocity. So displacement between 10 and 18. df minus di. It's going to be, looks like 6 minus 0. That's a positive one because that's sloping upwards. So the average velocity between 0 and 10. You know what I usually like to do? I usually like to use displacement over time, even though the slope works. It's the same thing. The displacement, we already found it, is negative 14. And the time is 10 seconds. So that gives me negative 1.4 meters per second. The average velocity between 10 and 18. Once again, I can say slope, or I can say displacement over time. Both work. The displacement here is 6 meters, and the time here is 8 seconds. So it's 0.75 meters per second. And finally, the average velocity between 0 and 18 seconds. There's only one way to do this. We can't find the slope because it's not one single straight line. It's going down and then going up. So we've got to use V equals D over T for this one. The displacement between 0 and 18, it's 6 minus 14. Final position minus initial position. The time is 18. So what is that? 6 minus 14 is negative 8 over 18, which is negative 4 over 9, which is negative 0.44. Good. Okay, let's take a look at number 4 now. This is a curved line, so there's not as much we can do with this. First thing we want to do is find the position at 6 seconds. We can do that. 6 seconds, we go up and over. We go up and over, it looks like it's about 3 meters. The position at 0 seconds is just 0. Position at 8 seconds, up and over, looks like it's about 5 meters. The displacement between 0 and 8, well, that's final minus initial position. 5 minus 0 is 5 meters. And the average velocity between 0 and 8, you can't use the slope here, but you can do V over T, or sorry, delta D over delta T, which is pretty much the same thing. 5 meters is my displacement. My time is 8. 5 divided by 8 is 0.625 meters per second. Okay? All right, I want to extend what we've just done here now to a curved line where we're asked for the instantaneous velocity. We see a curved line like this. We can find the average velocity of the entire trip or the displacement of the position at one moment in time. But how do we find the velocity at 5 seconds? What you don't want to do, and this is what people tend to want to do, tend to want to try at least, is say, okay, look, at 5 seconds, the position is 200, the time is 5, we'd say 200 divided by 5. That's wrong. Okay, that's unequivocally wrong. You can never find velocity by taking a single position in a single time. Velocity is what? It's not position over time. It's a rate, right? There's no rate here if you're just using one data point. Does that make sense? You can never, ever do that. So what do? Take a couple points? Well, what other point do we take, though? If we want to find the velocity at this point, 5 seconds, what other point do we take? 400 divided by 2? No. A good guess. We're going to draw what we call a tangent line. A tangent line at that point, 5 seconds. What do I mean by a tangent line? Let me give you a little analogy here, okay? You're down by the river. Here's the river. You throw a rock in the river. You throw it straight down, or pretty much straight down. What happens to that rock? It goes through only one point on the river, like in the water, but it goes right through into the water, right? That's not a tangent. Okay, that's not a tangent to the water. It's going through only one point. A tangent line, by the way, only goes through one point, but this wouldn't be a tangent line because it goes right through into the river. Okay, if I increase the angle at which I throw it here, that rock, well, then that rock, actually, if you were able to measure the angle at which it goes, it would actually change direction when it goes in the water because it changes speed. But it's still not a tangent line. It goes through one point, but it's not a tangent line because it doesn't skip off. If I increase the angle to almost like flush with the water, straight with the water, then that rock may actually skip off. That would be a tangent to the water. It touches one point on the water and skips right off. So a tangent line right here at 5 seconds has to go through one point and it has to kind of skip off. This would not be a good tangent line. It goes through only one point, but that's like the rock going straight into the water, right? This would not be a good tangent line. It's closer, but that's not skipping off, right? That's like the rock going into the water as well. We need a line that goes through only that one point, but skips off if that's the water. Kind of like this. Does that make sense? It skips off of that one data point right here, and sorry, it's touching only that one data point, and it's kind of skipping off following the curve. It's not going through anything else. Now, having said that, if this graph curved around like this, it would be okay to go through it up here because that's a different curve, right? So you don't need to ever worry about something like that. But on that one curve, it should go through only that one data point, and it should skip off that one data point. This isn't a perfect line because it should actually be over a little bit, like touching the blue line. Does that make sense? It's just kind of hard to draw it when you don't have a ruler here, that's all. The slope of it is pretty good, I think, still. I just should have it drawn over to the left a tiny little bit. Make sense? So what do you want to do here? To find the instantaneous velocity at a single point on a curved graph, a curved position versus time graph, you got to draw a tangent line. Now you know what a tangent line is. You got to draw it at one point, tangent line at one point, and then you got to calculate its slope. Or use v equals delta d over delta t. That gives us 2 points, right? If we have a straight line, even if it's a tangent straight line, then we can get 2 points from it and do displacement divided by time, or the slope. Once you've got your tangent line drawn on this graph, once you've got your own tangent line drawn on this graph, make sure it's long enough, and then pick 2 points on that tangent line, like maybe this point and this point, pick whatever points you want, I don't care. Pick whatever points you want. Just make sure they're far away. And then what do you think you're going to do with those 2 points? And well, yes, you're going to subtract them, but not just subtract them. You're going to say v is equal to delta d over delta t. Or you're going to say v is equal to the slope, delta y over delta x. Displacement here would be 1200 minus 0, because my final position is 1200, my initial position is 0. My time here would be, looks like about 12.5 seconds, 4 seconds. 1200 divided by 8.5 gives me about 140. Your number is going to be a bit different than that for a couple of reasons here. One, because I've drawn this by hand, right? Not with a ruler. Okay, your line is probably going to be better than mine because you're going to use a ruler. Secondly, the number is going to be a little bit different because this graph paper is not very good. You get this on a quiz or a test, you'll be given lots of increments, lots of vertical lines, lots of horizontal lines, so you can tell exactly where your points are. It's hard on this paper to tell exactly where you are. Okay. Thirdly, your line's going to be a little bit different than everybody else's. It's impossible for all of us to get exactly the same tangent line. We can all be close, but it's hard to be exact. So there's going to be a range here. There's going to be a range of answers. I think honestly, mine's a bit high. My number's a bit high here. Normally, I think we're going to get somewhere in that 120 range. You got what? I would say 80 would probably be the lower end there. 140 would be the upper. 133 sounds okay. I don't know exactly what it should be because, like you say, with I draw a tangent line by hand, I'm at the upper end here. Like I think I'm off a little bit here because of the way that I've drawn my tangent line by hand. But anywhere in that range, and you're probably doing okay there. Calculate that slope if you haven't done it already, or v equals delta d over delta t if you haven't done it already, and then try to get again somewhere in that range of 110, 120, 130, somewhere in that range.